welcome to our special fall 2024, winter 2024 Neocortex webinar. I'm Sergio Sanilevich. I'm the Director of Support for Scientific Applications at the Pittsburgh Supercomputing Center and the co-PI of Neocortex. I will be your master of ceremonies during these 3 hours. So just a few logistical things before we start. So first of all, as you've noticed, the webinar is being recorded, and that is so we can make the recording available to all of you and to the general public in a couple of days, as well as all the slides that we will be presenting. And then, while people speak, while our presenters speak, please make sure all your microphones are muted. And then at times after each segment or after each presentation, there will be Q&A opportunities. So at that time, you can certainly unmute if you want to ask a question yourself. But in general, whenever something occurs to you, please put your questions into the Zoom chat. We will be monitoring that. And there are some questions that we might be able to answer right away, but others would be then addressed in the Q&A periods after each segment. And also, because this is 3 hours, so we will have a break in the middle. But so again, we want to keep this interactive. So there will be polls that will be proposed during the presentations. And so please respond to those. And then finally, we abide by the Neocortex Code of Conduct, which we'll talk about in the next slide. And there's the link to it for the details. And then Paola, our Director of AI and Big Data and the Principal Investigator of Neocortex, and I myself are the ombudspeople. So if you have any issues that arise with regard to the Code of Conduct, please email us. And so with that, I think we are ready to begin, unless there are any questions regarding these logistical points.
I think we should be good, Sergio.
Okay, well then, let me turn things over to Paola Buitrago, our Director of AI and Big Data here at the PSC, and Principal Investigator of Neocortex. Paola, it's all yours.
Thank you, Sergio. Thank you very much for explaining the rules that we will use during our workshop/webinar. As Sergio pointed out, my name is Paola Buitrago. I am the Principal Investigator of Neocortex, and it's my pleasure to welcome you all to this workshop. So it's a 3-hour event, right? We'll have a number of talks. We'll have a group of speakers. We are going to have 2 speakers from the Pittsburgh Supercomputing Center, and then 2 speakers from the Cerebras Systems Corporation. So we'll have Leighton Wilson, who is our HPC Solutions Engineer, and also we'll have Sylvia Holland, who is a Machine Learning Solutions Engineer at Cerebras. Now from PSC, I will be giving some of the talks, but then we will also have Dana O'Connor, our machine learning research scientist, who works very closely with researchers in the Neocortex project. Now, going back to the agenda, all of you should have, if you're here, it's because you registered through the Zoom feature to register for this event, and then you had a chance to look at the agenda. As a recap, we are going to start with an overview of the Pittsburgh Supercomputing Center, a short overview for those of you who are maybe new to PSC. Then we'll have an overview of the project itself, so Neocortex. And then past that, we'll have a brief talk by Dana O'Connor regarding how to get a neocortex allocation. One of our main goals for this workshop is that you on one end understand and learn like what neocortex has to offer, if it's a good fit for the research that you're working on, and then if you have any questions, how to address them or how to get in contact with our team or the Cerebrus team in order to get a better sense of if neocortex is a good fit. And then should it be considered a good fit and of interest, then that you know how to gain access to neocortex. And there are a couple of paths for that we will be talking in the third talk that we have in the agenda. After that, we will do a deep dive in terms of how neocortex can support applications that are in the machine learning AI realm. And this talk at 2 p.m. will be delivered by Sylvia from Cerebrus. As that, we will have a short break, understanding that, well, we have a 3-hour event, so we'll have 10-15 minutes of break. And we'll follow up with a talk by Leighton regarding the use of neocortex for general purpose applications, right? This is beyond AI, what can be done or how neocortex can support any kind of applications using the Cerebrus SDK. Once we complete that talk, then we'll have a Q&A, kind of a general Q&A, and then closing remarks. But then as Sergio pointed out, after the conclusion of each of these sections, we'll have a couple minutes to take any questions that may arise. So with that, let's start with the overview of the Pittsburgh Supercomputing Center. It's a really quick one, just kind of a little piece of information regarding our center. This is where the Neocortex project is housed. The Pittsburgh Supercomputing Center has been enabling science and discovery since 1986, and with areas of expertise, of course, in high performance computing, anything related to data management, software architecture, implementation, and optimization. And then over the almost 40 years that the Supercomputing Center has been around, there have been a number of interesting breakthroughs that the systems that are hosted here have enabled. So since 1986, these are most of the systems. I think it's, well, it includes most of the most salient systems that have been hosted at PSC, starting with Cray XMP and Cray YMP in 1989, but then all the way to TMC machines and then Cray T3D and, well, Anton in 2010, Blacklight also in 2010. Then we had Bridges. It's more around the time that I joined the center. And then a deep focus on supporting data science, data management, and artificial intelligence later on with systems like Bridges AI and Neocortex and Bridges 2. We also, well, there are these two systems, Anton and Anton 2, right, that are focused more on molecular dynamics. So they are hardware optimized for this kind of workflows. And so they are, well, sponsored or like produced by D. Shaw. PSC is one of the few places where open science researchers can get access to this technology. So PSC has been focused on providing world-class computing resources. And so at this point in time, the systems that we offer are Bridges 2, Neocortex, and Anton 2. Today, we will be focusing mostly on Neocortex, so all the rest of the workshop will be anything and everything related to Neocortex. Bridges 2 in particular is more, is a heterogeneous type of system, and we have designed Neocortex in such a way that it works very well with Bridges 2, so if there is a complex scientific workflow that can leverage elements that are in Bridges 2 and also capabilities in Neocortex, that's something that is very straightforward. So we also want to encourage that type of use in our ecosystem. Now, Anton 2, as I mentioned, is more focused on molecular dynamics. And I understand at this time we are in the process of upgrading the system to what would be Anton 3. So that's very exciting for the type of research. PSC is also part of very large, important collaborations in the national ecosystem. So in particular is an important member of the Access program, supporting allocations and a number of other parts of the program. We also are part of the Trusted CI Center of Excellence in Cybersecurity, sponsored by NSF. But then we also play an important role in other collaborations that are funded by NIH, including the Brain Image Library, HubMap, whose goal is to have basically a Google Maps of the body, so store all the data at different levels of resolution related to the body, from cell level to tissue and organ level, and then send it. So very active also in important collaborations in the nation. Now, PSC also participates in the National AI Research Resource Program, which is at this time in the pilot stage. So we are part of the program as a resource provider. So Neocortex was one of the resources that have been available since the launch of the pilot program. Bridges 2 is also currently a system that can be accessed through NAIR. And we will be talking a little bit more about NAIR and how can someone request an allocation via NAIR. So I encourage you to, if it's a good fit for the NAIR program and you want to get access to Neocortex, that's the preferred approach to request an allocation. As you might be aware, well, NAIR is a national initiative to create or establish the research infrastructure that would allow researchers and students and academy world to advance different or all the activities that they would require in the future that are related to artificial intelligence. So what are the infrastructure capabilities that are needed in order to support all the development and discovery and research that is expected to occur in the nation, leveraging artificial intelligence. So it was launched earlier this year in January. It should be completing, well, in a month or so, will be, well, a month and a half, celebrating the first year of the pilot program. There are a number of projects that have joined Neocortex or have requested Neocortex resources through NAIR. And we are certainly very excited about this initiative. It's very much needed in the United States. Now, other areas in which PSC focuses their efforts, certainly training and education. In particular, there is this program that's called Adapt PA, through which we are working closely with teachers in colleges and academic institutions in the state of Pennsylvania, helping them incorporate PSC tools into their classroom, and also just helping them with curriculum development. So it has been focused on data analytics, machine learning, and additive manufacturing. We also have summer internships, and well, there's also other training opportunities, like, for example, the ByteBoost workshop, which is more related to Neocortex and innovative AI technologies. And also we have the workshops that we deliver via the wide area classroom on machine learning and HPC skill sets. Now, some examples of the projects that are advancing in PSC. This is already a year or so old, well, a little more. But then, for instance, prediction of hurricane flooding impacts. This is an image from the predictions for Hurricane Ian, right? But then working closely with the University of North Carolina, Chapel Hill, and the War Institute of Golf, we have researchers leverage systems like Bridges 2 to produce real-time predictions that will help with emergency management and will allow decision makers to recommend evacuation protocols or not, like, and what areas to evacuate. So this is a very important time sensitive and critical capability that Bridges 2 has made available. Now, other examples, this is a project by a group of researchers in Carnegie Mellon University, where the goal is to do route planning for a shared vehicle of fleets that are electric. And the idea is to develop, or they have worked on developing or doing data analysis of data from rideshare programs like Uber and Lyft. And then they work on creating, well, planning the routes of like what's optimal in terms of consuming less energy, right? So with with the intention of minimizing also social costs, like congestion, collisions, and emissions. Yeah, so other research projects that are advanced at PSC. This one is sponsored or well supported by Anton. And this one is about understanding a protein in the brain that is called IGLUR that is critical for the management of certain forms of epilepsy. So through a group of chemists from Carnegie Mellon University using Anton 2 and the Bridges 2 system, we're able to run a number of simulations that help reveal the step-by-step activation path of this very important critical protein. And the goal here is to identify future drug targets or treatment options that can help better manage this health condition, as I mentioned. So PSC is a national supercomputing center. It serves the national research community through NSF and NIH-funded projects, but also other complementary projects. A very important, an important message that sometimes is a well-kept secret, which is 100% free or has no cost for anybody advancing open science research. We have a number of research projects and a wide array of collaborators, and we're always welcoming opportunities to collaborate. So if any of these systems that I mentioned are of interest, please feel free to get in contact both with me or all other members of the PSC team. Now, with that, that's my quick overview of PSC. I want to maybe pause to see if there's any questions regarding PSC. But now that we have gone through PSC, we can dive deeper into what Neocortex has to offer. I see that we don't have any questions, or do we? Oh, we have some comments, but regarding our...
No questions as such. Going once, going twice.
Okay, very good. So we are going to go ahead with the Neocortex overview. So it is my pleasure to once again be here joining this webinar, right, and talk about Neocortex. So with Sergio, we have been leading this project for a number of years. So I'm me in the role of principal investigator, Sergio as co-principal investigator. And what the questions that I would like us to address, or by the end of this quick overview of Neocortex, what I would like us all to be able to answer is, what is this what is Neocortex? What is the program, the project? What are its goals? It would be great that we all know what is the innovative hardware that a researcher can get access through this project. Very important as well that we know what type of applications are supported by the system. So the system is very powerful and interesting for certain type of research. So not every research or not every type of application is necessarily a good fit. So getting a better understanding of what is the criteria and conditions that makes an application a good fit for Neocortex it's a very important message or goal for this talk. Also very important, how can we gain access to Neocortex? What's the evaluation criteria? What are kind of some of the expectations regarding the effort or maybe a skill set that a Neocortex researcher should have? And like an allocation, what does it entail? Also very important is how to get additional information and support from our team. So let's start with the Neocortex program, kind of high-level description. So Neocortex is an NSF-funded project that was delivered or has been delivered in collaboration with Cerebras and Hewlett-Packard Enterprise and the Pittsburgh Supercomputing Center. The image that we have here show like the Cerebras systems that are included, and also a server that is called the HP Superdome Flex, and that is also part of Neocortex. We have a picture of Bridges 2 because, as I mentioned earlier, Bridges 2 is tightly integrated with Neocortex. So then they use cases that leverage both Bridges 2 and Neocortex are ideal. So something to highlight is, as mentioned, like Neocortex is an NSF-funded system. So it was proposed in response to solicitation 19587. and in particular is a category 2 type of system, which is an innovative prototype of testbed. So Neocortex aims to capture very innovative hardware technology that was originally designed for artificial intelligence, accelerating AI training, but over time it has been found to be very promising and valuable for not only AI training, but inferencing and also general purpose type of applications. We will learn more about that in the upcoming talks. So Neocortex, well, this is the award number, so 25597. It's through the Office of Advanced Cyber Infrastructure. And as mentioned again, it's delivered through Cerebras and Hewlett-Packard Enterprise. So the goals of the project is to deploy this system, operate the system for 5 years. We are currently about to complete operation year number 3. And then our goal is to make these technologies available to the community, engage a wider audience, and foster the adoption of the technology, but also clearly identify where does the technology shine and what are some of the limitations, or what kind of use cases are not necessarily a good fit. When we proposed Neocortex, these were some of the use cases. So we wanted to make sure we had the technology needed to transform and accelerate AI-enabled research, but also fundamental AI research. So as we all know, well, AI is very compute and data hungry. So making sure that the compute capabilities were there for our community is what drove or motivated this project. With having the compute capabilities required, the goal is that we enable the creation of new or more efficient AI algorithms, foster the integration of artificial intelligence with other scientific workflows. So then this tight coupling of Neocortex and Bridges 2 is certainly responding to this goal. For sure, democratizing the access to game-changing compute power. And for our community, that's a critical goal of the project. And of course, exploring the goal, like the capabilities of this technology, and well, a number of other kind of goals and use cases, including supporting large-scale memory needs through the Superdome Flex, and well, really being focused very user-centric and making sure like the system, it offers new technology, but it's also usable and it meets the researchers where they are needing that. So Neocortex, this is how Neocortex looks like. And so this is what the system has to offer. So we have 2 Cerebras CS2 servers that are tightly coupled with an HP Superdome Flex. Each of the Cerebras servers has hundreds of thousands of cores. So each of them here has 850,000 cores, 2.6 trillion transistors, 40 gigabytes of aggregated memory, and 20 petabytes of memory bandwidth aggregated as well. And then they are tightly coupled at 1.2 terabits per second with the Superdome Flex, which in itself is a very powerful machine with 205 terabytes of NVMe SSD and 24 terabytes of RAM. So any application needing a lot of memory, maybe applications that only require kind of high memory, they're also welcoming the Neocortex ecosystem, even if they don't need Cerebras, full access to the Cerebras servers, or only the HP Superdome Flex. So as mentioned, Neocortex is coupled with or like integrated with Bridges 2 at the data level, and then we have a channel of 1.6 terabits per second between Bridges 2 and Neocortex. We also have been working on workflow management systems that talk with 2 of these very powerful supercomputers in order to facilitate the execution of complex workflows that leverage these 2. So something important to highlight, and then it will come again in the talks that we'll have later by Cerebras, is that we currently have the Cerebras CS2 servers. And Cerebra's latest generation of the Cerebras server is the CS3. So we are actively working on having Neocortex integrate what will be the latest version of the Cerebras servers. But for now, Neocortex offers what is the CS2, and that has some implications that we will learn more about in a little bit. Now, let's jump to the type of applications that are supported by the Neocortex system. And so this is one of the outcomes that from our initial portion of the project, right? So when we started Neocortex, there was that question, like what kind of applications are supported? And so we identified four clear defined type of applications. The first is the Cerebras model SU ML model. So someone that wants to use any of the 13 currently supported models in the model SU, which are also tied to the fact that we have the CS2 machines. So these are different flavors of BERT, GPT-2, GPT-3, GPT-J, Roberta, T5 transformer. And then we also have fully connected MNIS and then two-dimensional UNet. So a lot of focus on transformer type of architectures, but also a couple fully connected, well, the fully connected and the UNet machines. This is for applications that are machine learning specific, and then they currently support PyTorch and TensorFlow. Considering that we have the CS2 machine, well, the use of PyTorch is preferred since the next generation of Cerebras. It's only supports PyTorch. So all of these models are available in our documentation. Once you hit on any or like click on any of these models, you can go on there well, get more information about the model, including the architecture and some examples of applications that are supported. The other type of application that is supported, the second one would be models that are similar to those existing in the model SU, right? And that might require little adjustments that are a combination of the building blocks that are currently used by the model SU models. We do have a list of what would be those building blocks that are supported. But yeah, the idea is that the models that are used by researchers are as close, will resemble as much as possible those in the model SU if there are specific functionality that needs to be incorporated. Like that's normally a conversation we have with the PSC experts and also Cerebras experts to understand what's the best way to approach it. Third type of application is that will be general purpose. This is beyond AI. So it's analogous to coding with CUDA on NVIDIA GPUs. So you will be leveraging a general purpose SDK offered by Cerebras. And this one requires more effort than the first two type of applications. The first two type of applications is basically you are taking a model and deploying it and bringing your data and running on the system. So the effort involved is mostly about minor migration effort, depending on where your code is. But then here with the general purpose SDK, it would be, for the most part, coding as if you were using CUDA for deploying a code on GPUs. And we will learn more about this from later on in the upcoming presentation. Now, there is a fourth type of application that leverages the WFA, which is an API developed by NETL. And it's specifically designed for systems or codes that will discretize their space and then are solving kind of partial differential equations. So it can be used for machine learning, but then it cannot be necessarily integrated with what would be the first and second type of application. So those are the type of applications. Please feel free to post any questions you may have. I'm gonna looking at the clock, and so I'm gonna go next to briefly describing how can a researcher gain access to a Neocortex program, and then we'll have Dana dive deeper on the options. So there are a number of opportunities to access Neocortex as a researcher, but in particular, we have three different paths. First, we have the NAIR pilot program. As I mentioned, the NAIR pilot program is this national initiative, right, to design and procure the hardware and infrastructure and capabilities that researchers and educators will need to realize the promise of AI in education and research. Neocortex is a resource that supports this program. We also have Access, which is the Advanced Cyber Infrastructure Coordination Ecosystem. It's open to all US-based university and nonprofit researchers. Both NAIR and Access are offered at no cost. Applications are welcome on a rolling basis for Access, and there are different types of applications that Dana will describe in more detail in a little bit. Now, there is a third path for those researchers that don't meet maybe the requirements to apply through the NAIR program or Access program, and have an interest to get access to Neocortex. We can consider doing or granting discretionary awards, but then for that, we invite you to contact us at neocortex@psc.edu, indicating the kind of work you want to do. And also, of course, we will be discussing like what are the limitations of in general. So we will explore if it can be supported in case NAIR and Access are not good channels for, or are not good paths for you to get access to Neocortex. So I won't go into more detail here because Dana is gonna give us a presentation and is gonna show us clearly how to apply through the first two paths. But then if you're interested in the third part, please feel free to get in contact through an email. Now, coming towards the end of the presentation, this is just a quick overview. As I mentioned, the next presentations will give us way more information on machine learning applications, general purpose applications, how to get access. But then very important to keep in mind, like how to get support, right? Like even if you're an existing, even for existing and potential users, right? If you're interested and want to learn more about Neocortex or want to consider an idea for Neocortex, we have a number of channels or mechanisms through which you can get support and get in contact with our team and also with Cerebras. So then for starters, we would like to invite you to keep track of follow the updates that we will be publishing through our Neocortex website. We have a mailing list where we will be notifying of any updates or like any new opportunities that are made available through Neocortex. We have a Slack community that really encourage you all to join, where you could just send quick questions that will get really fast responses to your questions. Anybody can join in our community. You don't need to be a Neocortex user. Just if you have any question regarding Neocortex, this is a great way to get them addressed. We also have weekly virtual office hours. They are on Wednesday at 2 p.m. So we invite you to join these office hours. We also give the opportunity of a project, or like we give the opportunity to request a 30-minute personalized session, which would include one PSC expert and one Cerebras expert. And normally if you hit this link, you will go to a calendar where you can just select what option works for you, for your with your availability. If you share some information regarding what type of questions you would want to address or need help with, that would allow us to better identify who, like what kind of expertise to make sure is available in your personalized session. But I think this is also a great resource. So great opportunity, for example, if you have an idea and want to kind of come and talk with our experts at PSC and Cerebras and kind of scope out how would the project run on Neocortex. This is a great opportunity. And also for any related questions, comments, requests, neocortex@psc.edu, an email to that email address is an excellent way to reach out to our team. So with that, as always, big thank you and a lot of gratitude to our collaborators, Cerebras and Hewlett Packard Enterprise, of course, to NSF, who has funded this project, and our PSC team, which continues to make Neocortex a great success. So then I think this is the end of my talk. If there are specific questions, I'm happy to take them. Let's see.
So Dana is next then?
Yes, and I see there are a couple questions regarding support for JAGs and support for LAMPs, and that
Yeah, I think they're being addressed.
Yes. So I invite everybody to also review the chat and see the feedback or like responses that have been received by.
Or, you know, since Leighton has been addressing those, I don't know if you want to say something to everybody about them, about that, Leighton, or
Well, I will say on the topic of lamps, I'm happy to talk a little bit more about you know, those sorts of applications and mapping them to the wafer in my section.
yeah, thank you.
That's a great idea. Okay, so with that, let's move on to a deep dive on how to get a neocortex allocation. So Dana, I'll hand it over to you.
All right. Thank you, Paula. So just to briefly introduce myself, I'm Dana O'Connor. I'm a machine learning research scientist here at PSC. I work on the AI and big data group. And so I work on research and research support for Neocortex as part of my job. So a brief overview of what we're going to go over is how to actually get an allocation on Neocortex through both access and the NAIR channel. And then there is that discretionary channel that Paula mentioned previously. So the first one we'll go over is access. So what is access? This was established by the NSF to support researchers and educators with access to the nation's most advanced computing systems. So it's a bit of a consortium between all of these publicly available NSF-sponsored systems. And the big takeaway for access is that it does not cost researchers anything to perform research on these systems because they are funded through the taxpayers through NSF. So people who are eligible for an allocation are US-based researchers or educators at the grad student level or higher. If you are an undergraduate student, you do need to be under the supervision of a PI that is at the graduate student level or higher, but undergraduate students are still able to access these systems through PIs that have an allocation. You are also able to get an allocation if you are an employee of a nonprofit, non-academic organization like a museum or a library, a federally funded research and development center, a military service academy, since that's technically considered a nonprofit academic organization. And even commercial organizations are able to apply for access allocations. They just have to be willing to acknowledge that because this is taxpayer and federally funded, that you have to be able to publish your work in open forums such as GitHub repos and conferences and journal articles that are peer reviewed as well. So that is who is eligible for access and why access was established. So next slide, please. So for access allocations, how does it work? So users are usually granted credits, which can then be exchanged for service units or SUs on any of the access resources. So for example, if you have a bunch of access credits, you can exchange them for CS2 hours on Neocortex, GPU hours on Bridges 2 GPUs, or CPU hours on Bridges 2 CPUs if we were going to use the PSC ecosystem as an example. And the number of credits to the number of service units is determined based on the dollar amounts of those service units. So you're able to say that I was able to save this much money by using the access resources because I have this many credits. But again, this is a free resource. So that dollar amount is just kind of for you to get a handle of how much money you're saving and how many compute hours you have there. Some resources, such as Neocortex, will ask you to justify your request as well. For example, as we discussed in the last presentation, you're going to have to detail which of the 4 tracks you are planning to use. So again, track 1 and 2 are general and ML applications. Track 3 is the Cerebrus SDK. And then track 4, which I don't believe we'll be talking about today, is the WFA API, which was developed by some people at the National Energy Technology Lab. And we're happy to talk more about track 4 as well in a later time. Next slide, please. So the way access works is that there are 4 different allocation levels. So Explore is for a small amount of resources geared towards newer researchers. So a lot of times these are experimentalists who are looking to run their first simulation and don't really need a ton of compute power to get that done. or even people who are just curious what kind of compute power is available on the different resources, they'll normally get an Explore allocation. And only an abstract is required. So you just have to give a brief description of your project. The Discover allocation is for more modest scale research, and for this you need a one-page description. So once you kind of get your footing in the Access ecosystem, you can apply for a Discover. Next is Accelerate, which will require more substantial resources, and that will also come with a 3 to 5 page description with a well-defined plan of how you plan to use these resources. The fourth allocation level is the Maximize. There's technically no upper limit on the award size that is able to be given for a Maximize, and it should represent significant research progress. And because of that, this is roughly equivalent to an NSF proposal in terms of rigor and length. And for this, you'll definitely want to include some supporting data for why you need the resources you do, such as benchmarks and some previous work, just to show the NSF and the reviewers on the panel why you need such an extensive amount of computational resources. And then for the timeline for applying for these projects, the Explore, Discover, and Accelerate can be applied at any time. Maximize, I believe, is a semi-annual schedule. So keep an eye out on the Access homepage through NSF for deadlines and details about how to apply for that Maximize allocation. We definitely recommend going with either an Explore or Discover for your first proposal, and save Maximize for after you've got more of an idea of what kind of computational support you'll need. Next slide, please. And now we'll have a video demo of how to get an Access allocation.
Okay, please let me know. Are you guys seeing the
Hi,
video?
it's
Yeah. Let's hope the audio works well. Let's go.
I think the audio is working. I heard a bit of it.
I'm about to hit play. Let's go.
Dana O'Connor from the Pittsburgh Supercomputing Center. And if you are here, you are wondering how to obtain an access allocation for Neocortex. So it's important to note before we start that this will require you to have a registered access ID. If you do not have an access ID, please see our previous video about how to create an access ID. Once you have your ID, you'll log in here and then click on allocations. And that should take you to all of the projects that you have on Access. But let's say that we want to request a new project. So we encourage you to read the documentation on Access about these different levels of projects. But for now, let's say that we've already explored Neocortex a bit and we want to get some more time on the computer for something like a Discover access allocation. So fill in the relevant information here. And then in the main document here, we're going to want to see some evidence of the usage that you're planning to do on Neocortex following one of our 4 tracks, which are covered in a previous video. So the 4 tracks are ML using the model zoo, ML using variations of the model zoo, SDK for the Cerebrus wafer scale engine, and then the WFA API. So please define what track you're using in your main document and how you think Neocortex can support you in accomplishing those goals in that track. And then once we submit our allocation, we should get a notification that we have in fact gotten an allocation. And then we go here to exchange credits for resources. We go to add another resource to your exchange. Select PSC Neocortex Cerebrus Wafer Scale Engine AI Accelerator, and then enter how many CS2 hours we want here. We also have to request storage on PSC Ocean, which is the shared file system between Neocortex and our other system, Bridges 2. We also have to request some time on the Neocortex Superdome Flex server. And then once we do that, we can briefly explain what we want these resources for. So training some models, running some simulations, and then we'll submit for approval. Once you exchange these credits, you should get an email from Access as well as PSC saying that your credit exchange was successful and give you some details on how to set up your account and maybe get started on Neocortex. And so that is how you get an access allocation for Neocortex and how you can exchange your credits for CS2 hours.
Give just one moment while we bring up the slides there.
All right. So now we'll move on to obtaining an allocation through the NAIR pilot. So we touched a bit on that briefly in the previous presentation. So just a reminder, NAIR stands for National Artificial Intelligence Research Resource. And the point of this is to connect US researchers and educators to computational data training and resources to advance AI research. And this is a cooperation with federal agencies as well as government and non-government partners. So a couple of those non-government partners are pictured here. So we have Meta, Hugging Face, Amazon Web Services, OpenAI, of course, Cerebras, who is here with us today. And the people who are eligible to apply for this program are US-based researchers and educators from US-based institutions, academic institutions, nonprofits, federal agencies, federally funded R&D centers, as well as startups and small businesses with federal grants. Similar to Access, if you are a commercial entity seeking to apply for an NAIR pilot allocation, you do have to be willing to publish your results in open forums. So kind of the same rules as Access. Next slide, please. So the areas of focus for NAIR are twofold. There are cross-cutting focus areas, so across disciplines and focused on applications of AI. So for example, the creation of foundation models for specific purposes, incorporating models into simulations, as well as privacy preserving methods. The next area is domain-specific focus areas. So societally relevant research on AI safety and security, cancer treatment and health outcomes, resilience and optimization of agricultural, water, and grid infrastructure, improving the design, control, and quality of advanced manufacturing, and addressing earth, environmental, and climate changes. So if you want to use AI models for either of these two focus areas, you are probably going to stand a good chance of at least getting a bit of a review from the NAIR pilot review committee. Next slide, please. So NAIR allocation proposals have the following structure. You need a scientific or technical goal that is about 1 page that includes plans and timetables, as well as publication plans, because again, you are going to have to share your results with the public. You also have to estimate the compute storage and other resources that you'll need, which should be roughly 1 page. So the scale and type of resources, as well as any supporting data such as benchmarks of showing your models running on different hardwares and why you might need more hardware or different hardware than you've already used. And then we also link to the specific page with FAQs from the NAIR pilot proposal website on this slide. And then for support needs, you can also request collaborations from resource providers. So you can request collaborations with private partners like OpenAI or Cerebras or AWS. You also have to know any restrictions that apply here, such as HIPAA. And then you also have to, of course, include your team and your team preparedness. And you can summarize that with a CV or bio sketch, and then just detail the other qualifications of the team there. And it's important to note here, just as with Access, these resources are available to you free of charge, which is a great thing to note here. So next slide, please. And then the documents that you'll need include a proposal document with a limit of 3 pages, a CV and bio sketch for the project and team lead. You can also attach a document of references that you cite in your proposal document, and please follow the formatting instructions listed on the link included in the slides. Next slide. And then now we'll have a demo of walking through the actual NAIR allocation process.
Yay.
Hi, it's Dana.
There you go.
Hi, it's Dana O'Connor from the Pittsburgh Supercomputing Center. And if you're here, you're wondering how to get a Neocortex allocation through the NEAR pilot. So if you go to nearpilot.org and then click on current opportunities and researcher resources call, you'll be taken to the following page and then click on this start your submission, which will lead you to here. So please fill in the requested information such as title, field of science, contact info, and any supporting grants. And then down here, we have the available resources. Click on PSC Neocortex Cerebrus Wafer Scale Engine AI Accelerator. So this is just some information about what the wafer scale engine is, and then enter the amount of CS2 hours you want. We usually start with 100, but please feel free to ask for more than that if you feel like your workflow calls for it. Here you'll describe your research team. So describe some experiences that the research team has that would make them a good fit for the wafer scale engine, data and total storage requirements. And then here, select one of our 4 tracks for using the wafer scale engine. More information about our different tracks can be found in our documentation and are discussed in previous videos. Then answer that you have gone through all of these questions, as well as any other comments you may have. After you do that, please upload the relevant documents. So the main document, the project lead, CV, bio sketch, or resume, as well as maybe some references. And then answer the following questions down here, and then click submit, and you've submitted your NEAR pilot allocation request.
Very good. Thank you, Dana. Do you have any more slides? I think that's the end of the section of how to apply. Is that right?
Yep, so that's how to apply for access and NEAR allocations for Neocortex. And then of course we have that third discretionary option if neither of those fit you.
Yeah, thank you, Dana. So here the message is it's very straightforward to apply to either access or NEAR, right? And then so please leverage these videos that are available for your consumption. And then we also have other short videos that help for example, with the or explaining more detail the track specific or the type of applications for Neocortex. But yeah, we do encourage you all to, start at least with the access application, right? Like that requires only an abstract. So only creating, the simplest way to get access to Neocortex would be through an access allocation that requires an abstract title. And then, of course, once you have created an access account, but then it's very straightforward. Our team stands ready to assist with any kind of question or doubt that you may have during the process. So we really encourage you to come and join Neocortex and use the machines and the technology we have in the system. So with that, Sergio, I think I'll let you continue.
All right. So first of all, questions, comments on what you've heard so far from Paula, from Dana? There's nothing in the chat, but if anybody wants to pose a live question, please do so. Okay, if not, let's go on. And it is our pleasure today and privilege to welcome Sylvia Howland. She is a machine learning solutions engineer at Cerebras Systems. Sylvia supports various national laboratories and user facilities to accelerate scientific research using Cerebras wafer scale hardware. And I believe today she will be talking about machine learning on Cerebras Systems. Sylvia, would you like to share your screen?
Absolutely. Good afternoon, everybody. Let me get that share up. And then something I forgot to mention in that bio is I am also Cerebras's main liaison to the NEAR pilot. So I collaborate with all sorts of folks. If you're interested in the NEAR, I am also in that sphere. Fun fact. Awesome. Okay. So today I'm going to be talking about the CS2s on Neocortex and how those apply to accelerating machine learning workloads. I'm going to start off with just an overview of the system. Then we're going to get into the machine learning specific applications, how it interfaces with existing deep learning frameworks that folks are probably familiar with, And then I believe the folks at Neocortex PSC will have a demo of how to use the system. Excellent. So CS2 overview, the double skip. Excellent. So basically, the system hierarchy from lowest to highest level is like so. Each wafer is comprised of a very large number of PEs, or processing elements, each of which has its own compute core, its own memory, and its own communication router. These are arranged on the wafer in this essentially 2D grid, each processing element obviously running its own computations and communicating with the processing elements directly adjacent to it. Leighton, I'm sure, will talk a lot more about this when he gets into the general purpose compute SDK. But essentially each wafer then is the build around of each of the two CS2 boxes, which, like the folks at PSC mentioned before, hook into the broader Neocortex system, that Superdome Flex server, and the networked file storage. And so in this sense, we can understand each CS2 is basically just a network-attached accelerator. And the Cerebras software stack is specifically going to be split between the Superdome Flex server and the CS2s. Basically, our sort of software chief role is going to compile the code, manage the CS2s, and then we're going to have a number of input workers are going to read in data, stream it through the input pipeline, and get that sent over to the CS2. And specifically, the CS2s are going to spit back out our loss outputs, all of our tensor summaries, our checkpoints, going to go from the CS2s back to the Superdome Flex. And this is going to be managed via a pretty standard Slurm job management system. And then in terms of developer resources, for ML developers, we have two chief reference points that are good to familiarize yourself with. We have our Model Zoo repository, which is going to, it's essentially the batteries included repository we have. We have a number of pre-existing model implementations that we support, layer APIs to make it easier to tweak models, implement your own, et cetera, all that good stuff, as well as our sort of main software docs. I've included links to both of these. If you go to either the Model Zoo or our docs pages, keep in mind you're going to want to be looking at the versions of those that point to the original Cerebras installation. Like the folks at PSC mentioned, here we're running an older version of our software stack, which hopefully I think we're putting together a talk at some point to introduce folks to. But as of right now, focusing on this older version of the software stack. We also have the Cerebras SDK and its associated docs, which Leighton will be getting into later this afternoon. Excellent. So that's an overview of the system. Obviously, if folks have specific questions, we'll be more than happy to get into those during the Q&A. But in terms of applying these systems for deep learning, this version of the software stack is going to support both TensorFlow and PyTorch. There was a little sidebar in the chat. Over time, we noticed the community really shifting into PyTorch, and so we followed suit and focused heavily on that. But currently, Neocortex does support TensorFlow and PyTorch. Both of these are built, or rather, we're building sort of our graph lowering process based off of the Accelerated Linear Algebra, or XLA, compilation framework. This is also used for things like Google's TPUs. So in both cases, both TensorFlow and PyTorch are going to compile your model to XLA, at which point in the next slide, we'll get into how we lower that onto the hardware. But specifically for TensorFlow, we have our own TF estimator class that we've implemented that fits into a relatively familiar abstraction in that framework. And then in PyTorch, we've provided wrappers for data loaders, modules, and sessions to cover all of the various sheaf components you use for building and executing a PyTorch model in that version of the framework. And so specifically, we now have the question, we get to implement transparently our models and workflows in our framework of choice. How does that actually get lowered onto the CS2? which, as we saw before, is this 2D grid of processing elements. They talk to each other in this very like mesh computing type fashion. What's the deal there? So basically, first step for the compiler side of things, we first essentially trace the compute graph from both either TensorFlow or PyTorch and convert that into the Cerebrus intermediate high-level representation, or the CIRH. At which point, essentially, we have our own kernel library of both hand-implemented and auto-generated kernels. We take that intermediate representation, figure out exactly how to replicate that graph using our kernels. If an op is unsupported, an error will get thrown up during compilation. But we have fairly robust support for a lot of common operations, at which point we have this essentially logical flow of the kernel graph. We can now turn that into an actual execution plan across all of these processing elements on the wafers. So essentially, if we imagine we have these very large fabrics, again, with hundreds of thousands of compute cores, these processing elements, we can imagine taking different chunks of the model, different subsets of the layers and other computations, distributing that spatially across the wafer, and then essentially feeding in our input data and activations into that mesh, and everything just kind of ripples out and communicates back and forth. There's a lot more to the communication model that, again, I'm sure Leighton will cover when he gets into the SDK. He can speak a lot better to the intricacies of that process. But essentially, trace compute graph from your deep learning framework of choice, convert that to a generic intermediate representation, match to our kernel library to figure out how all of the compute ops need to flow into a hardware execution plan. And finally, we link that to an executable that we can send to any number of systems. And because of this, this lets us program cluster scale resource, right? It doesn't matter if we have 1, 2, 32 CS2 devices. We can program our model and our workflow logically in PyTorch or TensorFlow as if we were on a single device. And then this Cerebrus compiler will prepare that for use with an arbitrary number of compute devices. And if anyone's familiar with trying to run GPU workloads for deep learning that scale, there's a lot of engineering overhead that can go into just the communication and distribution logic of how do I pipeline everything. My code and performance can radically change as the number of devices I have increases. And it's always our aim to make it as straightforward as possible to scale compute independently of the implementation of your model. Perfect. And so in terms of other key features of the software stack, support a number of different model architectures, mostly focused on transformers and sort of similar ops you need to get to transformers, things like multi-layer perceptrons, independent attention layers, all of that. And then in TensorFlow only, this version of the stack also supports limited functionality for UNet. But in general, the focus is very strongly on transformers, and we'll get into more of that here in a moment. But generally speaking, across both frameworks, you're going to be able to train and evaluate your transformer model of choice. You can leverage and export trained weights in either TensorFlow or PyTorch formats, which can be useful both for sharing models around, but also for running, if you have like an existing like downstream evaluation workflow, you can always train and evaluate on Cerebrus hardware and export for final evaluation or distribution in the format of your choice. Our stack also integrates quite cleanly with TensorBoard for all sorts of logging and monitoring your jobs. And when I mentioned before that we can essentially map different regions of the model across the processing elements on each wafer, if your model is smaller, we can actually support multiple replicas of the same model being stored on wafer at any given time, which can give us some significant speed boosts because we're able to do more operations and duplicates in memory. Excellent. So like I mentioned before, CS2 and by extension Neocortex is really going to be best suited for running transformer style models. These are going to be your GPTs, your llama type models, T5, BERTs, vision transformers, so on and so forth, which is a constraint, but we get a lot out of this, right? Especially because transformers have become more and more dominant in the deep learning space over time. Everything from classification, annotation tasks, generation, sequence to sequence mapping. Representation learning has been especially popular for biological sequences, both for genomics, epigenomics, proteomics. I'm helping right now a client working with whole cell gene expression profiling, and more, right? Transformers can handle pretty arbitrary set-to-set transformations, and a whole lot of tasks can be formulated under that representation. And specifically, we're able to use transformers on workloads that are historically built using non-transformer models, right? Over time, image classification has transitioned more and more from convolutional neural nets to VITs, vision transformers. Autoregressive GPT-like models have replaced RNNs and LSTMs over time. And then with a model like BERT, as long as you apply a custom adjacency attention mask to it, you can use it very similar to the way you would with something like a graph neural net for graph modeling. So again, focus is very much on transformer style models, but we can run all sorts of different architectural variations and custom tweaks to apply that to all sorts of different problem spaces. And this is a slightly older list, but even with the version of the hardware and software that's not necessarily our latest gen, these were all achievements that were done using CS2s essentially. Epigenomic models, like I said, pre-training for biomedical natural language processing, protein transfer learning, training BERT to understand smiles, chemical representations as opposed to natural language. There's a whole wide variety of different applications that we can accomplish with this focus on scaling up transformer models. And then finally, shouting out again, both the Cerebrus docs and our model zoo. Links to those are here, but also earlier in the presentation. And as a reminder, as you start to dive in and explore these, as long as you're looking at the original Cerebrus installation for both of these resources, that will correspond quite cleanly to our setup on Neocortex. And I believe now we have a demo, but also now and during the Q&A, I'll be happy to answer any questions in chat to the best of my ability.
I don't see any questions in chat as such, but if anybody wants to say something or ask Sylvia something before we delve into the demo. Sylvia, I guess everybody's waiting for the demo.
Perfect. I believe that is being run on your side of things.
All right, I'll play the demo now then.
Well, I believe this demo doesn't have much audio. However, what we are looking at is how to run a simple, well, train a machine learning model, right, using Jupyter notebooks. So then you can get access to Neocortex via Open On Demand. And then we have a sample Jupyter notebook that is available to any existing Neocortex user. So once I think it was shown like how to log in into the Open On Demand instance, which is on demand at neocortex.psc.edu, and gaining access to Open On Demand, and then creating that session that will allow you to run the Jupyter notebook. Is it playing right now, Dana?
Oh, I was gonna say, do you want me to try it again with, I had my headphones in, maybe that was why the audio wasn't playing.
Oh, were you listening to the audio?
Yeah, I could hear it, that's why I
Okay,
was,
we were not. So that
So
might
if we
have
go
been.
inside
okay,
the Getting Started notebook.
could you hear that? Oh, okay, I'll just start it over then,
Thank you, Dana.
yeah.
Sorry about the little.
All right, let's go through a simple example of how to run a model on Neocortex. So we're going to go to the Getting Started tutorial page. We're going to grab this link for a Jupyter notebook down here, and then we're going to go to Open On Demand. On the Jupyter notebook option, and launch. And then we're going to click Connect to Jupyter. We are now going to go to the terminal, and we are going to paste the command there, and we have now the Getting Started notebook. So if we go inside the Getting Started notebook, we're going to go through the fully connected MNIST example. So this is just an explanation about Neocortex and the tracks we offer. These are going to be setting some helper variables. So the important thing to change here is the account ID to the account that is registered for you. This is going to be your username. So whatever you SSH into Neocortex with. Here is where the Cerebrus container lives. Here are some of the directories that we have to mount when we launch the Singularity container. Here's telling the Singularity container also where some of your Python paths are. Here are some of the Slurm arguments we're going to use to launch jobs. And then this will retrieve the CSIP address to be able to run jobs on Neocortex. We next go through and pull the example code, the actual model zoo from the Cerebrus GitHub. And then we change into the folder where the SCMNIST example lives. So the structure of the code is that there is a configs params file, which has a YAML file that contains the model configuration. You can change these as you wish to get a different model or lead it to a different data set. Data.py is where the data pipeline functions are called. And then the model.py is where the model functions are called. Run.py wraps that all together, and then utils.py has a couple of helper scripts. So run is the thing that's actually going to call the functions that you're actually going to run on the machine. So if you would like to modify an example, the suggested order is to modify the model, the data, utils, params, and then finally the run is the thing that you would modify last. In most cases, you don't really need to modify the run function that much, but if you want to, you can. So the execution will happen over 3 different steps. Validate, this just makes sure that all of your layers are supported. Compile, make sure that you can generate something that can run on the CS2, and then the training will actually run the full training job. So that will actually take you through a couple of training steps, whereas compile is just going to make sure that the model is able to run on the CS2. So this is the validation step. So if we go down here, we see that we have mode train, validate only, important argument, and then it should look like this if run successfully. We're next going to compile the code. And again, we see that we have that compile only mode activated. And then the next thing we're going to do is actually run the training example. And so your output should look something like this. So we see that we have that run function and the loss printing out as a function of the number of steps. And when we get to the final number of steps, we should see this training finish with the number of examples and the amount of time. And then that is
Oh, all right. I guess that is the end of it. I don't know why the last 6 seconds aren't playing, but that is the end of the demo.
Okay, very good. Thank you, Dana. So once again, through this demo, the goal is to illustrate how easy it is to train a model using the Cerebras servers available on Neocortex. So all the slides and video recording of this session will be made available. To all of you, we encourage you once again to apply, so get an allocation Neocortex either via NAIR or Access, and also to use these resources, the documentation and the demo we just showed, to kind of get your first job running, to confirm like just become familiar with the environment and yeah, have that first success, which is just executing the first training job on the very interesting buffer scale engine from Cerebras. So with that, Sylvia, is there any additional material you wanted to share with us, or?
That is all I have for this, but I'm more than happy to answer folks' questions or chat more about different use cases, applications.
Sounds good. Thank you, Sylvia. So do we have any questions? I believe we don't have more questions here. So Sergio,
I think they've all been addressed.
okay. So we can
But-
go ahead and proceed Leighton's talk, or we had agreed to kind of have a short break after this section.
Yeah, we're a bit early, but I don't think we mind that.
That's
I
right.
think, yeah, it's up to you. I think we can take a break now. So, so that would be 15 minutes. So we reconvene at 2:35.
Sounds good. Yeah, let's have a quick break. And then,
Yep.
and at 2:35.
Yep.
Thank you.
Recording. Okay, let's get back to it in 1 minute. What I would ask everyone to think about is, now that you've had, 15 minutes to reflect on things, if you have any questions now regarding the preceding presentations. So that's the first thing I'm going to ask starting now. Any questions that have occurred to you during the break? Okay, well,
I've got a
if not,
question.
Yeah,
there's
there's
a
a
do.
raise.
okay.
Um, just kind of a very big picture question, and maybe kind of a basic one. I guess in my defense, I was a few minutes late joining, but I was kind of curious, like, what is the difference between, and like, let's say architecturally, what's the difference between Neocortex and say Bridges 2? Uh, I attended the Anton workshop or presentation a couple of months ago. It was very interesting, and it really stuck with me. How different Anton is because and the specific uses for it. So with Neocortex, I was just wondering, kind of in a nutshell, what distinguishes it from Bridges 2 as a resource?
I can say
Right.
a few things here, which
Yeah.
is I will be in a couple slides going into a bunch of detail about the architecture. Sergio can certainly speak a lot more about Bridges, but certainly Bridges is a much more traditional.
Yeah, so I mean, just big picture, Bridges 2 has CPU and GPU nodes, and as you probably have heard, and Leighton will explain further, Cerebras is not a GPU system. This is in a way it's similar to Anton, but again it's its own thing, and it's it's as different from, at least as different from Brutus 2 as Anton is. Let's put it this way.
Okay, thanks.
So I would like to add some comments on that question. So first, Dominic, thank you for your question. And just to summarize, Cerebra, well, Neocortex features 2 Cerebra servers, each with a Whopper scale engine, and these are accelerators that were already designed to accelerate, well, or to power AI training, right? So they offer in a single chip, like the compute capability that would normally be found in a cluster. So it's a very powerful system. Later we'll describe in more detail like what is inside each Whopper scale engine and why is it so powerful, but it's specifically designed for AI and has amazing compute capabilities that allows large AI models to be trained or like be fit in a single server. Like for those that don't fit there, there's also, well, in the next generations of the Cerebras technologies, additional, I mean, like mechanisms to run them in 1 or 2 of these servers. But later we'll talk more about that. But imagine Anton, but for AI. So that's a good way to see it. While Bridges 2 is more general purpose, traditional compute elements like the CPUs, GPUs, and some large memory nodes.
Great, thank you.
Now they are very complementary, so that's why we encourage users that want to leverage both Bridges 2 and Neocortex. Yeah, that's a great question. So thank you, Dominic. So with that, I think we should be good to go ahead and get started.
We also had
Good
a
luck.
question in the chat about AlphaFold on CS2, and I just wanted to address it to the whole workshop that we do not have AlphaFold currently on the CS2. That would have to be something that you would port over. So that would be like a track 2 application.
So Sylvia, some additional thoughts on maybe supporting AlphaFold with CS2? If you
I would be happy to have a follow-up conversation about what would need to go into that, but without deep diving into architecturally what's going on. It's hard to say at the top of my head, but always more than happy to get new models working on the stack.
Yeah, you'll also need to figure out how to do MSA, multiple sequence alignment, on the CS2, but that would be definitely an interesting thing to try.
So we have another question by M. Tragowski, which is about Neocortex and PSC getting a CS3. So we are in the process of, well, finding a mechanism to update the hardware in Neocortex so we can capture CS3s. We do have a limited path or like option for some Neocortex researchers right now to have access to CS3. So, but that's selected. Like if you have a project that requires the functionality that is on CS3, we still please do get in contact, because through our collaboration with Cerebra, we can make sure you still get the needs of your research project satisfied. So, well, that's the first question by M. Then the next one is, like regarding, it says, would that have a different ML-SU and other application support? And the answer to that is yes. So CS3 has additional models in their model SU, or supports additional models in the model SU. So it's like a technology that we want to capture in Neocortex. So, but as I mentioned, if you have a specific project that requires the model SU or models in the model SU that are supported by CS3, do still get in contact with that in Neocortex, because we have a way to facilitate that access. Hope that addresses the question, M. See, I don't see any other questions. So I think, Sergio, you're good to continue with the agenda of the workshop.
Yep, let me unmute. So you all have already met Leighton anecdotally because he's been very helpful, but now we can formally introduce him. So Leighton is a HPC solutions engineer at Cerebras, an engineer and software developer who contributes to the Cerebras SDK for low-level programming of the wafer scale engine. And Leighton also supports SDK users and special projects using Cerebras hardware. And I think, as he will tell you, you can do most anything if you go to the SDK, but he'll tell you more about what you have to do that. So Leighton, it's over to you.
Thanks, Sergio. Yeah, so I lead our Cerebras SDK efforts. The way that I will go through this and talk about the SDK, I think it's helpful to frame it with a deep dive into the architecture and kind of, you know, what's really special about the Cerebras system and how you can use our tools to leverage it. HPC is technically in my title, and we often frame the Cerebras SDK as being an HPC tool. But I find both a little misleading because really what it is an entry point into the lowest levels of programming the Cerebras machine. You can program anything. Neocortex and PSC have been incredible partners. We've had a lot of SDK users at Neocortex do some really cool work. I'll briefly highlight a few. But I think, you know, the way to kind of frame this in your head as I go into this is sort of like our CUDA. Like, what is it at the lowest level of the Cerebras machine to actually program it and do unique and interesting things with the hardware? You know, one reason this is really important to us, beyond just presenting like TensorFlow or PyTorch to an end user, is that you know, there's only so many applications that Cerebras can develop internally. And one of the things that made NVIDIA so successful with CUDA was putting tools in people's hands to let external researchers, completely unaffiliated with NVIDIA, figure out how to run new and interesting workloads and map new and interesting algorithms to the hardware. And that's exactly what we want to do with the SDK. We want to put tools in people's hands that let people see our architecture at the lowest level and see what kind of incredible things they can do with it. And we've certainly seen many incredible things. So to start off at a high level, this architecture. So it is the largest square that you can cut out of a TSMC wafer. So this is for the wafer scale engine 2, which is in Neocortex. There are one of these chips per system, and I'll show you a picture of the system. But some of the eye-popping numbers to think about when you look at this gigantic chip. There's 850,000 cores on it. These are complete, you know, von Neumann architecture cores. I mean, they are true independent compute cores. The memory architecture, instead of having like separate DRAM, is all completely interleaved onto the chip. So each one of those cores owns a little bank of memory. And because you can read and write to it so fast, we can get 20 petabytes per second of memory bandwidth across the whole chip. These cores also can communicate with each other. And if you aggregate up the total communication bandwidth across the chip, you get about 220 petabits per second of fabric bandwidth on chip. Of course, I'll just briefly mention some of the numbers for the wafer scale engine 3, our third generation chip. Biggest change here was moving from the TSMC 7 nanometer to 5 nanometer process, which allowed us to fit a few more cores and a few more memory. And there are some architecture changes, but they're fairly minor. Biggest thing is more cores, more memory. Chat question. What is the speed from one chip to the adjacent chip? And was there a... I think it's, okay. So actually, let me get back to that. So I'll answer that in about 3 slides. So roughly speaking, you can kind of think of 2 sorts of features of algorithms and applications that can potentially do very well in our architecture. One are applications where strong scaling is a problem, where your application scales poorly across nodes as you go to finer and finer grained parallelism. And the other are things that are constrained by data access, applications that are traditionally memory bound. We actually have a Gordon Bell finalist from supercomputing from each of the last 2 years that I think do a pretty good job of demonstrating each of these features. So the reason that we can do really well with applications that traditionally run into strong scaling limits is because we have such a fine-grained unit of parallelism. We have on the CS2 850,000 cores, and each core is connected to its 4 nearest neighbors and can send and receive data from a neighbor in a single cycle, which means in less than 2,000 cycles, you can go all the way from one end of the chip to the other. For data access, as I mentioned, we don't have separate DRAM. We just have 40 gigabytes of SRAM that is uniformly distributed across the wafer. Each core, each of those 850,000 cores owns 48 kilobytes of that and can read and write to it in a single cycle. So in a lot of applications, I mean, I think the classic one here, and we have a few use cases that I'll show where people have done this. You know, stencil-based PDE solver, something like a finite difference method, is a really classic example of something that is memory bound. Because often you're reading field values, you're doing a time step update on them, and then you're writing them back. So you have very, very low data reuse. Which means that on a more traditional architecture where you have some separate memory subsystem, your actual processing units are often sitting there twiddling their thumbs, you know, waiting to actually go read memory. And these architectures develop these like complicated cache hierarchies to try to alleviate this issue, but you still often have your cores just sitting there waiting, idling for stuff to be read from memory or written to memory. To the question about connection between chips, let me make sure that I got the word. So what is the speed from one chip to the adjacent chip? So to start off with, one chip. So this right here is a picture of a CS2 of a box. There is one chip per one of these boxes. Each one of these boxes is a third of a standard rack. So it's roughly 15 rack units. Coming out of the box are 1,200 gigabit Ethernet. So the total throughput to get off the box is 1.2 terabits per second. And this, of course, you know, in the case of Neocortex, is being fed into those Superdome Flex, those Superdome Flex HPE nodes. So the way that you should think about it isn't necessarily a specific like chip to chip speed, because we have data coming off these boxes onto commodity switches or commodity traditional servers, and then those servers also connected to a CSC. This is all just Ethernet, so it's just standard Ethernet.
Gon has amended his question.
Oh, one core to the adjacent core. Okay. I'll talk about that in detail, but one cycle. You can send a 32-bit packet from one core to an adjacent core in a single cycle. That'll be the next slide. I'll talk a bit more about that. So I was mentioning about how we can do really, really well on stencil-based PDE solvers, things like finite difference methods. The core feature of something like a finite difference method is sparsity, right? If you represent your entire grid and you have your matrix of the way the grid points interact with each other, you have this banded structure that's very, very sparse. The The same in some sense applies to sparse workloads in AI. At the end of the day, you can often think of sparsity as taking some dense operation, like a dense matrix product, and turning it into a whole bunch of vector scalar products. You know, when you zero out a bunch of entries in those matrices, you basically just end up with a bunch of vector scalar products. On GPU or CPU based architectures, the issue, of course, with having a whole bunch of vector scalar products is that you're not reusing your data a lot. Like you're reading this Y vector, you're reading this X vector, you're then computing and you're writing back to memory. You're only using these elements once. So you could think of it as you have 3 bytes of memory accesses per flop. So you have 2 reads and then 1 write per floating point operation that you perform. So on a traditional architecture, operations like this are going to be memory bound. Like you are not going to get the full utilization of your compute. And this is something that we can do incredibly well because of the memory architecture. So as I mentioned, there are 850,000 cores. They're laid out in a grid with each core, which we call these cores processing elements, connected to its 4 nearest neighbors. And these cores can send and receive 32-bit packets that we call wavelets to and from its 4 neighbors in a single cycle. These are bidirectional links. So it means in a single cycle, one of these processing elements can both send 32-bit messages to its 4 neighbors and receive 32-bit messages from its 4 neighbors, again, in one cycle. So that's how I got the less than 2,000 cycles calculation to send a message from a 32-bit message from a processing element here all the way to the other end of the architecture. If you just count out the number of hops it would take, that will be your upper limit. What is the clock rate on the WSE2? It is 850 megahertz. So the ones at PSC are running 850 megahertz. In terms of data type supported, we have native support for 16 and 32-bit floating point integer data types. Of course, we have some special AI-centric data types like bfloat16 and our own specially rolled cbfloat16, but we have IEEE 16 and 32-bit floating point. I'll talk a little bit about this processing element architecture. So here I've kind of done a zoomed in view of what one of these processing elements look like. You can think of this as consisting of 3 components. The processor, so like where the arithmetic logic units are and the control actually is, the memory, so this is that 48 kilobytes of memory that each processing element owns, and then the fabric router, which is responsible for sending and receiving data to the neighbors, to and from the neighbors. We also have this link here called the ramp, and the ramp is how you get those 32-bit packets, those wavelets, between your processing element and your fabric router. In terms of how you communicate, right? I mean, you have this incredibly huge grid. You have these links between your cores. But of course, if you think about how you might map a very complex program to this architecture, you have to think about how you can tag your data to make sure that it's used in the right operation. So this router is programmable. On top of our bidirectional links, we have static or dynamic virtual channels which specify routes across the fabric, which we call colors. And you basically can tag those 32-bit packets, the wavelets, with a color, and then this router will look at a little routing table and see for that color where it's supposed to send it, and then it will send it along the correct link. That 48 kilobytes of memory is data for the PE. It's also instructions. So the program running on this processing element is also in this memory. So a bit more detail about the compute at the risk of going in a bit too deep. I'll talk about our execution model. It's a data flow execution model. So there's little chunks of code on these processing elements called tasks. And they may be triggered by the arrival of a wavelet on a certain color. So maybe that task is associated with one of those routes with a certain color. When a wavelet comes in along that color, the processing element will consume it, and that task will be activated, and the data within that wavelet will be an argument to that task. These processing elements are individually programmable, which means in principle, not that you would want to do this, in principle, you can write a separate program for every single one of these cores. It does not have to be the same program. Truly can be a separate program on every core. We also, I think I saw another question come in. How many data packets can each process simultaneously? You mean how many data packets can each processing element process simultaneously? I assume. Okay, yeah. So each one of these cores, actually, I'll talk about that on I think the next slide. We'll have a nice picture. While I can talk about it in a bit more detail. One more thing I'll mention here before I get to that, though, is that these cores only have one main thread, which cannot be preempted. And so there's just this main thread of compute. These cores also have these little threads that we call microthreads, which are for asynchronous operations. So the reason you might want this is that when you are receiving data from the fabric or sending data to the fabric, you might not want your cores control logic sitting and waiting for the data to be ready to send, or sitting and waiting for receiving some data. So instead, with these little micro-threaded operations, you can do it in the background. And then whenever that operation is done, you can tell your core to then do something with that data. But it's a way to kind of break synchronicity between some operations occurring on your core, so you can allow them to occur in whatever order is allowed by the flow of data across your fabric. So as I mentioned, for routing, and I'll get your question here about processing wavelets, those data packets. So here is like a little simplified version of a routing table. So there are 24 of these virtual channels that we call colors on each processing element. And for each entry for a certain color, we basically have little check mark set for which direction wavelets along that color will be sent. So for instance, here's a little simplified routing table with 4 colors, and this is for the receive direction. For the send direction. So you see here, like, this blue color has east and south set. So what this means is that if the little compute element on the processing element, so the compute element is this part here, the processor, if it sends some data up to the router along the color blue, then that color blue will then multicast that data to the east and to the south. If it sends data up along this color purple, then it will send it to the north. You might be wondering about this ramp direction here. So there's the 4 cardinal directions to your neighbors. The ramp is what connects the router to your actual compute element on your processing element. So a send direction of ramp, a transmit direction of ramp, is basically what you're doing when you receive data. So this PE is expecting to receive data from a neighbor along this green color and then send it down the ramp. In one cycle, you can both send along each of these links and you can receive along each of these links. The router has these little queues called input and output queues, which help buffer your input and output wavelets along for along each of these directions, for each of the colors, I should say. And then in terms of getting down to the actual processing element, you will be able to send one element down or send one packet down from the router to the processing element in a cycle. It actually takes 7 cycles to do it, but you can do 1 per cycle. And then the router can receive 1 per cycle from the compute element. So it's very, very fine-grained communication. Does that answer your question about how many data packets each can process simultaneously? Okay, great. So a bit about the memory. So as I mentioned, and this is another really unique feature of our architecture, we don't have any separate DRAM. We just have the memory completely interleaved with our compute, where each processing element owns 48 kilobytes of memory. So this memory is not directly addressable by other processing elements. To send and receive, you have to access your memory and then send it along a color to a neighbor, so where that neighbor can process it. The same with, like, receiving data from a neighboring PE. But what's amazing about this memory is that you can read and write to it in a single cycle. In fact, you can read 128 bits and you can write 64 bits in a single cycle. So our compute path on the processor, like our actual arithmetic logic path, is completely matched to the memory. So what that means is, if we're doing something like an 16-bit add operation, in a single cycle of performing that operation, that single cycle includes reading the 2 16-bit operands from memory, computing on them, adding them together, and then writing them back to memory. So say y plus equals x. In a single cycle, we are doing all of reading x from memory, reading y from memory, adding x to y, writing y back to memory. Now, as I mentioned, we actually have we can do 128 bits of reads and 64 bits of writes per cycle. So if you have something like a 16-bit add operation and you do your math on it, you see that we can actually do 4 of those in a single cycle and match our memory, because for each one of those add operations, we read 16 bits plus 16 bits for each of the 2 operands, and then we write back 16 bits. So we read 32 bits and write 16 bits. But because of the width of our memory accesses, we can do 4 of those operations. 4 times 64 reads, and 4 times 32-bit reads, and 4 times 16-bit writes. So we can actually do 4 of those add operations in a single cycle. And again, that includes the reading from and writing to memory. So I know that's a fairly detailed and very, very fast overview of the architecture. We have a whole bunch more details online about how to program this, primarily via the documentation for our Cerebras SDK. So this is meant to be a general purpose parallel computing platform set of APIs for writing custom programs for the Cerebras architecture. It's built around a language called CSL, the Cerebras software language. I'll show some examples of this, but it's a C-ish language via Zig, which is one of the languages attempting to be a modern Zig. I suppose Zig is to C what Rust is to C++. Someone might get mad at me for saying that, but I think that's about the right analogy. But it's kind of meant to be some more type safe C, but it's very similar to C. And we use that for programming the individual processing elements. and also for handling the layout of our programs across the processing elements. We then have host APIs with Python. So you send data to and receive data from the chip using these Python APIs, and you launch your program on the chip using these Python APIs. We do have C++ host code as well. We simply have yet to document it and make it fully publicly available, but that's on our to-do list. We have a set of libraries that come with it. Some libraries that abstract away some common computational motifs. So one thing might be broadcasting data across a row of PEs or down a column of PEs, or doing a reduction operation across a row or column of PEs. So we have a library called collectives that will set up all the routing to do that sort of operation for you. We have other libraries that kind of wrap up some unique features of the architecture and are attempting to raise the level of abstraction a little bit. The SDK comes with a bunch of tools, most importantly, a simulator. So the whole SDK ships as a Singularity container, and it includes this simulator, which allows you to run the SDK, do a cycle accurate simulation of your program on any resource you have access to, which has Singularity or Aptainer installed on it. Neocortex is a great place to do this. And in addition to running on the hardware, you can also use the simulator to start building out your programs and exploring the mapping of your algorithms to the architecture. So the way the simulator works, as I said, it's cycle accurate. Of course, if you could do a cycle accurate simulation of the entire wafer very, very fast, then you probably wouldn't actually need the wafer. So often what people do is they create, little miniature programs. Maybe you start out with just one PE, and then you move to a fabric of like 10 by 20 or 5 by 5 processing elements to think about how your algorithm scales across the architecture and how you would map it to the cores. So I hinted at this a little bit, but it's helpful to kind of keep in your mind there's three components here to programming the machine. We have the PE programming language, CSL. This is the code that defines your tasks and how the PE reacts to receiving data along a given color along one of those virtual channels. We have a layout portion, which also is specified in CSL. This layout is what tells the compiler which program should go on which PE, and then what the data routing between the PEs, between the processing elements should be. And then we have our runtime component, the SDK runtime, which is what you use to move data to and from the device and to launch kernels that run on the device. I'll mention CSL is a language that's also used internally by our kernel engineers to write some of our optimized kernels in our machine learning stack. Most of that work is still done in Chasm, which is our assembler, Cerebrus assembler. But as CSL has matured as a language, we're using it more and more for internal implementation of kernels in our ML stack. So what does this look like from, I apologize, I meant to update all the 3s to 2s, but I missed it in a couple of places. So what does this look like from a programmer's perspective? Like a network attached accelerator. You have some host node where that's where you can communicate with your machine or with the simulator from that host node. You stream in data. The machine takes in that data, reacts to it. Your host code also can launch a particular kernel that runs on the device, and then your host program can also receive data back from the machine. So I'll talk a bit about the language, and I hope also gives you some sense of what some of the structures look like of writing a program in CSL and just programming the machine generally. So we have a whole bunch of the features that you would expect from any C-like language, with pretty straightforward and comprehensible syntax. I mean, we have a pretty clear type system. You can, of course, define functions. We have control structures like if statements and for loops and while loops and all that. We have this block. We have this thing called comp time, which basically allows you to wrap a whole chunk of code in this little comp time specifier, which just says I want all of this to be evaluated at compile time. And then we have a bunch of CSL specific features that are about getting the most out of this architecture, including this thing called data structure descriptors, which I'll talk about in a bit more detail. So in terms of familiar features, the type system, the syntax is very similar to what you would see in other modern languages. Float, signed int, unsigned int, 16 and 32-bit types, a Boolean with trailing type, and every single variable that you declare is specified as either var or const. You can create arrays, you can create pointers. Functions are just the Zig style syntax, where you have a trailing return type, but it's really a quite straightforward syntax. All the traditional control structures that you would expect. We have a for loop. We have both the C style for and like the kind of C++ style range for loop, which is super helpful, along with while loops with iterators, but nothing really that surprising in just the standard syntax of writing a code that runs on a individual processing element. Now, some comp time features, or some quality of life features. As I mentioned, we have this idea of comp time, which basically means that you can wrap some code in this little block called comp time, and it means that it will force evaluation of that block at compile time. Often the compiler is smart enough to figure out some things that it can evaluate completely at compile time, but this is a great way to force specification that something will be totally done and determined at compile time. We also have parameters which work a lot like kind of like a define preprocessor directive, but are strongly typed. So these have to be totally bound during compilation. The reason that these are very useful in your program is you can imagine that as you think about how you map your algorithm or your program to the architecture, that a lot of the processing elements are probably doing the same thing. Like you'll want to compile the same program to it. But maybe along like the left edge or the right edge of your fabric, the program is a little different. So maybe you'll have some parameter that's specifying, I'm compiling this PE program for the left edge of my fabric. So I need to do something a little different. And so you can parameterize these programs using these compile time determined values. We also have a module system. Any CSL source code file can work as a module. Modules are importable into other modules. So this is how you create code modularity for your processing for your PE programs. This is also how our libraries work. You import them as modules. When you import a module, it acts as an instance of a unique struct type, and you can import a module multiple times and it'll act as a separate instance of a struct. So you can imagine like this teeny tiny module right here, that all it has is some global variable X, and again, this is all PE codes. This is all something happening on a single processing element. So you have some global variable X, and then you have some function called increment, which will add 1 to X. You can imagine here in your PE program that you import this module twice, and you import one instance with the name v1, one with the name v2. When you call increment on v1, it does not in any way impact v2. So you have two instances of X here in your PE program, one that lives in the v1 module, one that lives in the v2 module. So if you call increment on v1, it'll only affect v1.x. If you call increment on v2, it'll only affect v2.x. Being able to import a module multiple times and acting as kind of unique instances of a struct turns out to be a very, very helpful feature. Okay, so now some special features related to getting the most out of the architecture, and also a first example of what it actually looks like to have a task, have a chunk of code that reacts to data being sent or received across the fabric. So built-ins, we actually get this from Zig as well, similar to function calls, but they kind of invoke special compiler functionality. Some are very simple things like this zeros right here. All this zeros does right here is it says that we're going to initialize this matrix, this tensor, this 4x5 tensor with all zeros. So we both declare and initialize it to all zeros. Tasks are the core building block of CSL programs. You can think of them kind of like functions, but really they're just chunks of code that are triggered by incoming wavelets on a specific color. You also, in the flow of your own code, can write a little built-in that says activate task, and then that task will be activated and will be run next when the current task finishes. So I have a little example here that kind of shows you what this looks like for data flow across the architecture. So inside this comp time block, I have two built-in calls, this bind task and this set local color config. So what is this? Well, the bind task right here is saying that I have some task named rec of task, and I have some color, which I've specified, named rec of color. Rec of task is going to be bound to rec of color. So rec of task will be activated whenever we receive a wavelet along the fabric that has color rec of color. We then need to actually give some routing at compile time to that color rec of color. So here we have RX from the west and TX down the ramp. So the RX and TX directions are from the perspective of your PE's router. So what this says is that my PE expects to receive wavelets from the west along rec of color, and then transmits them down the ramp to my compute element. So what happens here is that, draw it out. So we have a PE here. We have a PE here. They are, I'll just draw the fabric like this. So what happens is that this PE's router will receive a wavelet along the color rec of color from the west, and then transmit it down the ramp to the compute element. The compute element will then feed in that piece of data as an argument to rec of task. And so rec of task will take the data within that wavelet as an argument, and it will set global value equal to the value of data. And so global value is just some variable that lives in our PE. So say that wavelet contained the value 5, then we'll receive the value 5, transmit it down to the compute element where it will activate this task. And then that task will receive that value 5 and set global value equal to 5. Okay. How do I, let me turn off the drawing so it does not. Okay. Data structure descriptors. So this is a very, very important piece of our architecture. And I think highlights the way that our architecture is very kind of tensor centric in the way that we think about data operations. So these data structure descriptors, they provide a mechanism to consider an array or a tensor, just any chunk of memory in your processing element, as bound together with some access pattern to that memory. When we have operations that use data structure descriptors, they will run for multiple cycles to complete an instruction on all data referenced by that by the DSD. So I'll start out here by taking a look at these 3 DSDs. So somewhere above this little chunk of code, we've defined 3 arrays, 3 chunks of memory, DST, source 0, and source 1. All this tensor access expression says here is that we are starting from 0, going to access the first 5 elements of the DST array. This source 0 DSD says that we're just going to access the first 5 elements of the source 0 array. This source 1 DSD says that we're going to access the first 5 elements of the source 1 array. So when I have this little operation here, this f_add_h, so this is a half precision floating point add. I have my destination operand first, and then my source operands afterwards. So you see that I have 2 source operands, source 0 DSD and source 1 DSD, and then 1 destination operand, DST, DSD. So what does this operation do? It performs an element-wise add of the 5 elements in source 0 to the 5 elements in source 1, and then it writes them to DST. So this actually lowers to a single instruction on the architecture. And this single instruction will run for however many cycles it needs to run to complete this element-wise add. As I mentioned with our memory architecture, we actually can do 4 f_adds, half precision adds in a single cycle. So this entire operation of grabbing elements from memory to add, performing the addition, and then writing them back to memory, we will process all 5 of these elements in 2 cycles. 1 cycle to do the first 4, and then 1 cycle to do the last. So this whole operation of reading the 5 elements from memory from both of these arrays, adding them, writing them back to DST, this whole operation completes in 2 cycles. DSDs are a unifying concept in that in addition to giving us a way to access memory with these access patterns, they also are a way that we can read and write to the fabric. So where we can actually read wavelets from the fabric, in addition to having tasks that receive them, we can read them from the fabric with the DSD. We can write them to the fabric with the DSD. So in this example right here, I have what's called a fab out DSD. This is how we send data to the fabric. We have some color associated with it, output color. So this fMoveH operation, what it's going to do is it's going to loop over the 5 elements of DST referenced by this DSD, and it's going to send them out to the fabric along the color output color. And this will take about 5 cycles to complete to have them all sent to the fabric. And then once they're being sent up to the router, they then travel along whatever the specified path is for output color along the fabric. Okay, so that's a bit about what the programming model looks like for the individual PEs. With our SDK, we provide a whole bunch of example programs, including introductory tutorials that are growing every day, and some more and more complex examples. Some are quite simple. Some get quite involved and complex. The ship with our SDK, they are all installed for anyone to use on Neocortex. We also have a GitHub repository that has all of these examples. We have more than what's listed here, and they're growing. I just wrote a little I think a very instructive Conway's Game of Life example using the SDK that I'm hoping to ship out with our next SDK release, which should be in a week or so here. So getting access, of course, the SDK is available at Neocortex on PSC resources, but you also can get access locally to using the simulator. We have a page that says release announcements, but it's actually also you can access and download the SDK for yourself and then sign up for release announcements as well. We have a public documentation page, that's a great question. What are the issues if you need more than 40 gigabytes on the wafer? So at the risk of I don't want to, but I'll yeah. So I'll talk about this. So leaving the SDK aside, in terms of our approach to doing AI models on the architecture for training or for inference, with the installation that we have at the Pittsburgh Supercomputing Center, we have a pipeline mapping of models to the architecture. So what that means is that for any given model, you are constrained by the memory, by the amount of memory on the chip, which means that for the mode of operation that we have at Neocortex, there are limits to how big your model can get. With our current installations, our newer installations, we have this approach called weight streaming for doing training. With weight streaming, we kind of invert the approach a little bit. So in weight streaming, your activations stay present on the wafer, but your weights are streamed in one layer at a time. So you have a bunch of CPU servers, which are very, very high memory that hold your weights. So we've kind of disaggregated where we keep memory weights away from the compute on the wafer. That allows you to arbitrarily scale up your model size, and also gives a very simple data parallel mapping to running on multiple systems. I mentioned that just to kind of give some context about kind of what our modern approach is with the CS3 and installations with the CS3 to doing model training. But it is the case that with our installation here and with our CS2 installations like this, there is a limit in the software to how big your models can get. We do also have now kind of a brand new inference capability for LLMs with CS3s and our new software stack. In that case, we actually do the pipelining, which means that if you have you can do the math figure out, if you have a really large model, you might need multiple CS machines to hold the model. And so you'll have, your autoregressive inference occur with the samples going through multiple machines and then looping back around through the machines. I hope I didn't throw too much out there in answering that question, because there's lots of different pieces. But I think there was bet made in the early days that models wouldn't become very, very huge, and then they did become very, very huge. And we had to rethink our approach of how we map models to the architecture for our newer generations of solution. Okay, so a bit about, so I want to spend a little bit of time. I'll show you running something on the wafer, but I want to spend a little bit of time talking about some ways people that have used the SDK. We were a year ago, the SDK was still under NDA and not generally publicly available unless you had access to a place like PSC. We've opened it up so that anyone can download it now. And as I said, our goal of the SDK is to put tools in people's hands and let them do interesting things with it. Not directed by us, right? Just letting people figure out what they can do with the architecture. And PSC has been a big partner in that. I've circled a few projects here. I need to update the slide with more images because we have others that have come in. But these are some that have used Neocortex resources. So more chat questions. Are there plans to integrate Cerebrus SDK with OpenACC, OpenMP offload? That's a absolutely fantastic question. We have had some very, very early exploration into looking at OpenMP offload. It is not a trivial problem, and it requires a lot of engineering work. The reason being that the nature of this architecture is quite a bit different, right? And we also have that limited code space. We have to think very carefully about both how we map something to a spatial architecture and how we manage and how we manage our limited resources on the processing elements. What I will say is there have been some research groups, and Dirk and his wafer field application tools is a good example of this, at trying to look at how we can represent some common computational motifs, particularly that occur in scientific computing use cases, and map that at a much higher, like provide to end users a much higher level entry point to mapping it to the architecture. At Total Energies, we had some work done by a student at Total and at Rice, who built this Python front end called StencilPy for mapping stencil operations to the wafer. I mean, really finite difference in finite volume methods with regular grids. We've also had some students, so grad students at EPCC, Edinburgh Parallel Computing Center, and TU Berlin have been working on a CSL backend to a tool called XDSL, which is this MLIR dialect for representing primarily stencils, but other similar kind of operations. So there have been a lot of early efforts to think about what is the right way to map a lot of very common motifs to the architecture, such that end user can just take a higher level input, like the National Energy Technology Laboratories WFA, or the StencilPy work that Total did, or this XDSL work that that was done by that is being done by EPCC and TU Berlin. All that to say is that OpenMP offload is certainly something I would love, but it is admittedly a large challenge. Do your libraries include 64-bit, 128-bit floating or fixed point arithmetic? So again, we don't have any native support for 64-bit or 128-bit, but that being said, we do have an example program that ships with the SDK that shows you how to do kind of, arbitrary precision. I mean, just doing the bit shifting and stuff to get it to work. We have it on. We have not shipped a library for this yet, but we've had it on our backlog to add a not quite 64-bit emulation, but like a float, which I think comes out to more like 48-bit precision. But we've had on our backlog to add higher precision emulation using something like float. But we do not have that as libraries yet. We have some examples that do something along those lines, but we don't have it as a library. I will, admittedly, it does come with a fairly large cost to emulate higher precision numbers, particularly because we can't really make use of those data structure descriptors for doing these vector operations with those precisions. So I expected I'd probably go very deep into the architecture, but I will mention a quick couple things that end users have done. We've had a long-standing collaboration with Total Energies. This started out with us writing code jointly with them. It's turned into them writing code on their own. They're primarily working on seismic processing algorithms. But they've developed quite a few stencil codes with very large speed ups over GPU architectures. We had some from SC23 comparing to A100s. We now have some work comparing to H100s, including this finite volume solver that applies some of their work on carbon capture and storage, where they achieve 210x speed over a single H100 on a CS2. And the StencilPy I mentioned, where they're able to just in Python represent this stencil and it automatically generated the CSL code, where for this seismic acoustic wave propagation, they achieve 95x speed up over an H100. These papers have appeared at SC24 now, and search Cerebrus, you can find them. We had a Gordon Bell Prize finalist last year with KAUST, which is about seismic processing. What's really cool about this is that there was a piece of this algorithm that was very, very, very memory bound. With 48 CS2 systems, we were able to achieve a sustained memory bandwidth comparable to the entirety of Frontier, higher than Frontier's, comparable to Fugaku. Not number one anymore. I need to update these numbers for the latest version of the SC list, but comparable to the largest supercomputers in the world. So 10x the performance for a tenth the cost on this particular algorithm. We had work that was done at Oregon National Laboratory on Monte Carlo particle transport. This is a really cool paper looking at mapping a very specific piece of Monte Carlo particle transport. This really expensive operation. That's this cross-section table lookups. There's all these like little cross-section values. You need to look them up from the table to aggregate your like probabilities of a nuclear interaction occurring. And they achieved 180x over a single A100. And again, this was using a CS2, not a CS3. We recently had a very exciting paper that we did with San Diego National Lab as a 2024 Gordon Bell Prize finalist. These numbers are much higher now. We've actually are now at about 750x faster than Frontier. And this is using a single CS2, 700x faster than you can do on the entirety of the Frontier supercomputer, for doing and now I believe it's a 900,000 atom simulation of tungsten using the embedded atom model. So it's a fairly small potential, but it's appropriate for metallic systems. The reason that we can have such a ridiculous X factor over the entirety of Frontier is that for this problem size, you very, very quickly run into a strong scaling problem on Frontier, where you have fairly fat nodes. And after only throwing a few nodes at it, you throw any more nodes at the problem, you go from receiving diminishing return speed up to actually receiving negative speed up. And we can do such fine-grained strong scaling across our architecture that we can get these very, very high speed ups. So I want to very quickly talk about what running on Neocortex looks like. So there's really basically three ways to run. You can run your programs in the simulator just directly from the command line. You can submit a Slurm job to the just to Neocortex's Slurm scheduler for doing a simulator run. And you do the same thing, submitting a Slurm job that reserves one of the systems for a hardware run. So I'm not going to go into the details of the program, but I do want to show you. So here I'm at a let me clear this out to make it a bit cleaner. So this is one of those example programs. So as I said, we ship a bunch of examples. They're available on Neocortex, including these tutorials and more complicated benchmark examples. I'll go into this simple tutorial program here. You can find these programs with detailed walkthroughs in our public documentation at sdk.cerebrus.net. So this tutorial one here is the program I'm running. And this walks through in quite a bit of detail what this program is doing, what the various commands are, and kind of how this is actually communicating with the system, launching a kernel, moving data back and forth. So all of our examples ship with this little commands file that all it does is include the compile command and then a run command. The compile command specifies the dimension of the fabric. So if I'm running in the simulator, I might be running on a teeny tiny fabric, like an 8x3 fabric. And the CS Python, like I said, the SDK ships in a singularity container. This is just calling the Python inside the singularity container that then runs the program. This is a very small program, so I can run on the login node, though, of course, anyone who's used communal computing resources in general, you probably shouldn't run things, certainly nothing big on a login node. Well, I just ran this program before. Yeah, there we go. And we just compile a program and run it and check the results correct. But we also have these Slurm scripts for submitting a simulator program to one of the CPU nodes, one of the Superdome Flex nodes at Neocortex, but also one for running on hardware. And if you look at the difference between these two scripts, you can see the difference between the compile command for hardware and the run command for hardware. The only difference in the compile command is we specify the exact fabric dimensions of the programmable fabric on this machine, versus our teeny tiny fabric that we specified for our simulator program. And then for our run command, we specify the IP address of the CS machine. So the IP address that we actually use to connect and communicate with the CS machine. And of course, it's just a Slurm script. I can submit it. I'll submit the simulator one. And you can submit it and watch it run like any Slurm job. Okay. Yeah, so I just wanted to show that it's actually quite straightforward to do all this on the Neocortex system, to compile for simulator or for hardware, and to run for simulator or for hardware. This is a bonus example that I'm not planning on walking through. I just want to provide it with the slides so people can take a look at this after the fact if they're interested, and free to ask me questions. So about this. So with that, I am finished, and I'm happy to take any questions about any of this.
All right. Thank you very much, Leighton. Questions for Leighton? Maybe to give you a bit more time to ponder, I think we're going to have like an exercise for you, Paula. You want to launch those polls?
Yeah, well, while we wait to get some questions, then we are going to launch the questions that later on you propose for the audience, right? So it's a quick poll with 3 questions related to maybe the level of experience with similar low-level programming approaches, also what frameworks or APIs do you use to when running parallelism in your code, and also what kind of scientific workloads or algorithms are you interested in. So we welcome your input regarding these 3 specific areas. So they are very short questions. But then, yeah, thank you, Leighton. Thank you very much for this very thorough and comprehensive talk regarding the architecture of the Warper Scale engine, and also how it operates and the SDK, and also showing us how to run a simple application, for example, using the SDK on Neocortex. So Leighton is fantastic to work with if you guys want to if you get to have an application on Neocortex that leverages the SDK, you will be working directly with Leighton and his team, and they're just really good to work with. So highly recommend it. So that's one of the bonus if you apply for an SDK project. You get to work with Leighton.
But I would say that in general, you know, when Paula mentioned and the various ways to contact us, as a matter of course, like, you know, for our 30-minute office hours that are dedicated to your project, when you call those, then depending on the topic, but you know, we always are able to get Cerebras engineers, whether it be on SDK or on machine learning. So so by working with, and also the Slack channels that were mentioned, they're also monitored by our friends at Cerebras. So
that's right. So the Slack community channel, well, workspace, you can join it, and over there you can get access to Leighton and also our team at PSC, but also the team in Cerebras that handles machine learning use cases, so Sylvia and her colleagues. So even if you're not an existing Neocortex users, so you can through a Slack get access to Leighton and others at Cerebras and PSC to maybe consider or explore how well a project would work on Neocortex or with the Cerebras SDK, or the Model Zoo or the Track 2, which is similar models as the Model Zoo. But then on top of that, as Sergio pointed out, right, like that personalized session that we talked about earlier, right, requesting half an hour with someone in Cerebras and someone from PSC. That's also available to anyone in our community. if you're considering Neocortex. That's a great resource. Okay, so I see that we have 10 responses so far. So let's see, shall we leave the poll a little bit open for a little bit more? Do we have any other questions?
There are some questions, yeah.
Oh yeah, we have some good questions.
So Don wants to make a comment.
Thank you. Thank you, everyone. This is very interesting. Just had actually two quick comments. One is that the architecture of the fabric is very much, the individual cores are very much like the transputer devices of the 1990s, if anyone is familiar with them. They had a 32-bit device with 4 or 6 high-speed links that you could just plug into other transputers. And the communication across whatever fabric you put together was, I'm sure they faced the same kinds of problems, although the scale was much smaller because you couldn't put together reasonably, 100,000 of them or however many you've got. I just thought that was really interesting. The other thing is that the device is obviously ideal for doing very fast vector arithmetic. And, you obviously, HP obviously made a decision to go with 32-bit hardware oriented towards AI, but it would be really nice if there was a smaller fabric, even a linear fabric, configured as a systolic array that could handle up to 128-bit is what we really need. I mean, I'm just a thought.
Those are some, particularly the analogy to the transputer is quite interesting. I think is very well taken. Yeah, on the I can't say anything about our roadmap, but I will say that we're definitely very aware that there's lots of really cool use cases for the some of the fundamentals of this architecture that take advantage of higher precision arithmetic.
Okay, and then there's a question from Rajat.
Yeah, so the expected learning. So I also, when I did my when I did my thesis, the vast majority of what I did was in OpenACC because it allowed me to get up and running much faster than it would have to use CUDA. I won't sugarcoat it in that depending on the sort of application that you're trying to map to the architecture, the learning curve can be quite high, just in that a lot of kind of how you approach the architecture and mapping your problems to it is quite different than what you would do with a GPU, and there's a different set of concerns you have to think about. Now, there are other concerns that you no longer have to think about, like if you're trying to really optimize your code, you no longer really have to think about managing your caches at all. For instance, I think we've done a pretty good job on trying to reduce the learning curve by improving the documentation. It's not perfect. We definitely have a ways to go to get it to the ideal, to get it to the ideal state. But we think that we are improving the learning experience of using this architecture.
You did mention the efforts to kind of devise higher level
That's
access
exactly
by
right.
higher level languages. So
That's exactly right. Yeah. Using Python like don't seem as on.
So later, I'm gonna conclude this poll now. You can share the results, but yeah, as you address the next question, I'm gonna share the other poll that Sylvia prepared, right? Like 3 other questions. These are more related to machine learning. So for those of you that are interested in machine learning applications, please address this other poll, and then later on, please proceed with addressing the other question that is in the chat.
Okay, yeah. So using Python libraries like NumPy and SciPy. So we don't have support for like generically using NumPy or SciPy on the architecture. So that's not something we have support for. You know, when it comes to Python libraries, our support is the limited sets of PyTorch necessary to support the models that that you saw Sylvia talk about. So we don't have support for using NumPy or SciPy on the architecture. Now, that being said, of course, say that you're using the SDK, the Cerebrus SDK, so you're writing your own host code for for launching programs on the machine and copying data to and from the machine. Your host code, you certainly might use NumPy and SciPy, but that would be running on an x86 CPU. Dual precision so I'll kind of rephrase the second half of your question to say like how would a dual precision calculation perform if you were to map it to the architecture. So again, we have the problem that we don't have native support for dual precision. You know, depending on your application, if you had something that was terribly, awfully memory bound on a GPU, and you instead had a way to do it where you smartly emulated dual precision on our architecture, then it's possible we could get better performance. It's also possible if you have something that on a GPU is traditionally very, very compute bound, and that has very high data reuse, and then you tried to do like dual precision emulation on our architecture to do it, we would probably have much worse performance than a GPU. Like that would not be a great use of the architecture. But I'm trying to see how I can look at the polls. I'm not sure how I can see the responses.
Paula, can you?
That would be a question for Rias. I'm not sure where so right now we have the models workflows poll up.
Yeah, maybe we can try after we end this poll, then there might be a way to share all the results then.
Okay. Want to do that now, or should we keep it open still, like maybe 1 minute? Let's keep it 1 more minute.
Yeah. If we don't have any other questions, I think we can go ahead with the closing remarks. She's very...
Well, do you want to look at the polls first?
Okay, well, we have 10 responses for this poll. So let's give
Let's end this one and see if we
so-
can retrieve the previous one. Share results. How about that? Can we do about those polls? Riaz thinks about that. Maybe Paula, you want to give us your closing remarks?
Yeah, they're very short and sweet. So first, I'm gonna just the one slide. So I want to thank our speakers, both from PSC and Cerebrus. Thank you so much, Leighton and Sylvia, for the great talks that you guys shared today, and also Dana. And thank you, Sergio, for facilitating the workshop, and also Riaz for all the logistics around organizing this workshop. So as kind of big 2 important messages and takeaways as for those of you that are still in the audience, just a reminder that the process to get a Neocortex allocation is very simple and straightforward. We had Dana illustrate how can you get an allocation via NAIR, and also how to get an allocation via Access. And also, if you're interested in a discretionary allocation, right, that like do get in contact with us via the project email address, neocortex@psc.edu. Now, as you're applying for an allocation or you're considering Neocortex, so you have any follow-up questions after this workshop, We invite you to use any of the support channels that we have, which are the Slack community. The link is in the documentation, but also will be available in the slides that are going to be published after this workshop. There are the weekly office hours we talk about Wednesday afternoons at 2 p.m. Eastern time. And we also have personalized sessions that you can just request. So will you go and there's a Calendly feature that allows you to select what time works for you. If you let us know you want to talk about SDK, we'll make sure to get in contact with Leighton and have him or someone from his team join. Then we also have very good comprehensive documentation, so that's a great resource. And for anything else that you may need, comments or anything that you want to share regarding the project, questions, suggestions, to email us at neocortex@psc.edu. So my call to action is, after you have received all this great information, I invite you to apply for a Neocortex allocation, right? So it would be fantastic that each and all of you get a Neocortex allocation, even if it's the small one via Access that just requires a title and an abstract. If you have any questions as you're applying, please use any of the 4 channels that I just highlighted. We are happy to help and address any question you may have. So with that, thank you everybody for your attendance. There are no other questions. Do we have any additional questions or?
As we said, I think we will let everybody know when the
poll results?
recording, the recording and the slides are up, and maybe we'll find a way to also post the polls when we do that, like on the same page. So
That's great. Very good. Yep, we'll be following up with information, with sharing the recording, the slides, and also poll results for everybody that attended. So thank you so much.
thank you.
I think this is great timing, everybody, speakers and and Sergio, our MC. So thank you all. Enjoy the rest of your
See you all
Friday.
on Neocortex soon.
Yeah, looking forward to that. Thank you all.
Happy weekend.
Everybody.